All right, folks, here we go. We're getting more into this kinetics. I'm real excited about this stuff. So as you can see, I've got the Math 3 model up here, all right? And so I'm going to kind of be teaching side by side with these things. I'm going to work out, the equations on my board here. And then I'm going to be showing you how it connects to these models that you're doing, all right? And some of the things, some of the examples that I'm going to show you here are a little bit more detailed than what I'm asking you to do in the assignment. So I'll point that out when I've added things to this Math 3 assignment that you're not required to do, okay? So let's get into it. So first order reaction. So in a first order reaction, and what we need to assume here for now is we're not really calling this a mechanism. We're not really calling this a total step. We can just think of this as a very simple elementary step, a fundamental step, okay? And so for a first order reaction, we could say that A goes to products at rate constant K. Okay, so you can see here on my Mathematica model, I just said A goes to B with rate constant K. Same thing as just saying A goes to products. Okay, and so we're saying that we know that this is a first order reaction, or we're imposing it's a first order reaction. Okay, so when I go to write the rate law of this reaction, that's the first way that I start. Okay, I start by saying dA by dt. And when I consider the stoichiometric coefficient, right? Remember, we did all of that stuff, if I back up for just a minute, right when we talked about these relative rates, technically the reactant should be negative dA dt, right? So let's put that in there. Okay, here we go. So I'm going to say negative dA dt equals, and it's going to be the rate constant times the concentration of A. And since we're saying we know this is a first order reaction, we know that this is really A raised to the first power, okay? So now so this is my rate law, okay? And this is a differential equation, believe it or not, all right? So if I rearrange this, and I'm gonna write this as dA dt equals negative K times A, all right, so if I call T equal to X and concentration equal to Y, just to make this a little bit simpler to view, then this is a differential equation of the form dy dx equals negative K times Y, okay? And as it turns out, we can solve this. I'm going to solve this equation next, okay? But as this becomes more complicated, as we build in more complicated reactions, we can't solve these types of differential equations with an analytical equation. We have to do a numerical solution. And I'll explain that into the Mathematica file soon here. Okay? So another way that I could write this, just to give us some familiarity here, if we know that y is a function of x, I should say. Actually, yeah, let's make sure that I'm consistent. Just using my simple notation to indicate that this is a differential equation, then I could rewrite this as y prime of x equals negative K y of x, right? So I can write this in the same way, where dy dx is the same as saying y prime of x equals negative K times y of x. Okay, that's what makes this differential. So now going back to this, if I want to solve this for the integrated rate law, then what I need to do is get the like terms with the like terms. So I'm going to move A next to dA, right? So that's going to go dA over A. And I want to integrate that from the initial concentration, A0, to the concentration at any time t. It could be the final time, but we're just going to say generic anytime t, okay? And so that's this side. And so I just divided A over to this side, and now we multiply dt over to this side, and so that becomes the integral from 0, right, A, 0 times 0, to just t. We're integrating it from 0 to any arbitrary time t, and that's going to be negative k dt. Okay? So this is a very easy differential equation to solve. So we're basically, right, if you notice here my line, these are all the same equation. It's just writing it in a different notation. Okay? So now I can solve this all day. I know the integral of this side is the natural log, and when I apply the limits, that's going to be the natural log of a at time t over a initial. And the integral from 0 to t of negative k dt is very easy. That's just negative k times t. Okay? And so now I can rearrange this in several ways, and I'm going to write all of those down right here. So several ways to write the first order integrated rate law. So I'll start by rearranging this one. And when I rearrange that, I get the natural log of a at time t. And I'm going to do a couple of steps here, okay? So I'm going to separate these out because I know that I can write the fraction as a subtraction for natural logs, right? And so that still equals negative kt. So rearranging further, if I say natural log of a at time t, that equals negative kt plus the natural log of a0. And now if I were to plot the natural log of a versus time, I will get a straight line with a negative slope. And the slope of that line is the rate constant. Okay? So we always view rate constants as positive. Rate constants are always positive, but because of the negative sign in that equation, there's a negative slope. Okay, so this becomes a y equals negative mx plus b, right? And the fact that this is decaying tells us the reactant's concentration is decreasing in time. Okay, so now there's another way I can rearrange this equation, and I hope that I've given myself enough room here. So I'm going to take the e of both sides, and when I do that, I get, so let's box these things up so we know which equations we want. So this is a good equation to know for first order. Okay, the linear form. All right. And now the form that I like to use more than the linear form, so if I take e of both sides, right, then I just simply get at over a0 equals e to the negative kt. Okay? And what I really like about this equation here, man, I'm getting sloppy with my work. Sorry, folks. There's another way I can also rearrange this, like the following: at equals a0 e to the negative kt. Okay, so both of those are acceptable. And what I really like about this one with the at over a0, those become relative concentration units. Okay, so man, oh man, oh man, I was too sloppy writing my notes. Okay, so basically, in other words, at time 0, at the start of the reaction, this ratio will be 1.0, right? Because at time 0, AT is the same as A0, the initial concentration. So I really like this because you don't have to know the absolute concentration. And as you'll see in experiments, this is really useful. So you don't have to have a calibrated determination of concentration if you can determine the relative concentration. So now let's move over to this model, okay? And so you notice here, the linear form is this natural log versus time, which gives us a straight line. But here what I've got plotted, okay, so I just said call A0 1 molar and B0 0 molar, okay? And then what we get now, so really I'm looking at like this version, Even though I'm starting at 1 molar, it looks like it's, the relative version. But now if you look at the profile for A, that's an exponential decay. So first order reactions are exponential decays. Okay? So now what about the rate law for the product? Okay? Well, I said up here, right, if I was really interested in, let's say dB by dt, right, that's just going to be positive K times A. We still think of it in terms of the reactant when I write the rate law. It's all about the reactants. Now, where did the positive come from? Well, because we recognize that B will have a +1 stoichiometric coefficient, right? So that's where if I know the reactant is dA dt equals negative Ka, and I have this simple reaction, the simple first order A goes to B, then the rate law of the product is just going to be dB by dt equals positive K still times A. Because in rate laws, it's all about the reactants. So let's check out my lines of code here. Okay, so I gave you these lines of code, but I'm going to show you where these come from. Okay, so ND-solve is the numerical solution to the differential equation. We didn't need the numerical solution here because you can see we got this very nice, simple exponential relationship. However, the numerical solution will still give us the correct answer. And when the reactions get more complicated, we don't get a perfect equation like this. We have to solve numerically, okay? So now what I have, so that's what that ND means, numerical differential solve. And look, A prime T. Well, that A prime T is the same thing as dA by dt, right? And now notice I use the double equal sign. And I use the double equal sign because I want a numerical solution, not a function solution. So that's why I'm not using that colon equal sign to give me the hard function. I want this to be like a solve the right-hand side of the equation based on the left-hand side of the equation. That's what the double equal sign means. Okay, so now you notice here, it's just negative K times A of T. So here I just wrote A bracket, but that's why I wrote it up here like this. So I'll write it in the same way I wrote my Mathematica, right? It's A prime of T equals negative K times A of T, right? It's the same thing as this, okay? So that's this line, all right? A prime of T equals negative K times A of T. And then look, now we can do it for B. And look, B prime of T is going to equal positive K times A of T, just like we came up with here, okay? And now other conditions that we have to put in, still the double equal sign because we're doing this numerical solve. We're saying call the initial concentration, so the concentration of A when T equals 0, we're saying call it 1 molar. We're saying B at time 0 equals 0 molar. And then now this is going to solve the solutions for A and B over this total time window that I set up right here. All right? And so now when I go to evaluate that model, before I can plot it, first it has to be evaluated. And I'm going to evaluate it for the concentration of A at time t, and I'm also going to evaluate it for the concentration of B at time t. And now look, these are all codes that we've used before. So I called this entire line here that I've highlighted Model 1. That's Model 1. So now look at my syntax here, okay? I'm saying plot, evaluate this list, just A and B. If we had more reactants, maybe reactant C, reactant D, reactant E, etc., I would include those in the list. And now we remember that this means replace. And so I'm saying replace these solutions with Model 1. And Model 1 is right there, okay? And now I say plot from t equals 0 to 5, plot range all, and then beautiful, we can see reactant decay, product evolution. And now what I've done to highlight the role of the rate constant, and this is extra. You don't have to do this in your model. But what I did here now was created a manipulate model for this first order reaction. And if you follow my hierarchy here, it's manipulate, plot, evaluate, right? These solutions. But now what I did was, instead of putting in model 1, so see, notice here, I do replace and then replace with model 1. So instead of doing that, I just say replace, and then I just recopied that entire model 1 code, which takes me all the way up to there. So that's the same thing as saying model 1, but now it goes comma, and I'm going to say let k be manipulated from 0 to 5, and my units here are inverse minutes. Okay? So now this is pretty cool. I love this. This is what I love about this Kinetica model. So now I have the rate constant turned off. And so to do that, right, don't forget to push that positive sign. So the rate constant's at 0. So you can see A is just over the 5 minutes, not reacting at all. But now this is really cool. As I increase the rate constant, you can see a bigger rate constant owes to a faster reaction. And look, if I take that all the way up to 5 1/minutes for the value of that rate constant, which I'm going to be talking about these units soon here, okay? Then you can see the reaction is over with very fast, right? And once A is reacted away, then B gets the corresponding correct stoichiometry, right? Now the concentration of B is 1.0. And once again, just to see that, if I slow the reaction down by decreasing the value of the rate constant, then the reaction takes longer to complete. So at that point now, I made the rate constant about 1/5 as much, and it takes about 5 times longer for the reaction to go, okay? So let's talk about time constants. So still first order reactions, but now let's talk about time constants, okay? So I'm going to write this in a couple different ways. First, I'm going to start by saying natural log of A at time t over A0 equals negative k times t, all right? So if t equals seconds, then k must be 1/2, or just simply 1/time, right? Because when I have a natural log, the units go away. So that means the right-hand side of the equation has to also be unitless. So whatever unit time is in, let's say hours or days, the first order rate constant has to be 1 over that base unit, okay? So this is the first time constant. We should know the rate constant, the units, for a first order is always 1/seconds or 1/time. So it's a frequency, really, when you think about it, okay? So now what about some other time constants? Well, one that you're aware of is called the half-life, and we usually make that t 1/2, okay? And I can get to the half-life by saying A at time t equals 1/2 of A initially. So that's the definition of half-life, okay? And when I substitute that into this equation, right, I can say now the natural log of 1/2 of A0 over A0 equals negative kt, all right? And so when I do that, this becomes the natural log of 1/2 equals negative kt. And if I want to get rid of that negative sign, then this becomes, that's going to flip this. And so that just makes it natural log of 2 equals kt. And you know what? I'm going to put a t 1/2 right there so we know that that's specific to the half-life, okay? And so now I can say that the half-life for a first order reaction is natural log of 2 divided by k. Natural log of 2 is 0.693. You may have remembered this from Chem 110. Okay? So half-life for a first order reaction. All right, and you can see because it's 1 over k, a large k owes to a small half-life. So that's the same way as saying a large k is a fast reaction, which is like what I showed you right here, right? When I jack k way up, the reaction gets much slower, or faster, excuse me, okay? So now there's another time constant that you've probably not heard before, but it's commonly used in atmospheric and environmental chemistry because it's really useful. So let's underline half-life, and that is called the lifetime. And lifetime gets a Greek letter tau, okay? And I think lifetime is far more useful than half-life for a first-order reaction. And here's the reason for that. So in a first-order reaction, when you think about it, there is technically an infinite number of half-lives, right? This thing just keeps decaying and decaying and decaying and decaying and decaying, right? So you can just keep getting half to half to half to half to half to half to half, okay? So that's, the half-life is kind of useful when you're talking about maybe you only want to know one half-life, right? That gets you to 50%. But look, the next half-life would get you to 25%. And then the next half-life is 12.5%. See what I mean? Like it just keeps scaling it in half. So what becomes useful, I think, is the lifetime, okay? And so lifetime, we'll define that now. A at time t equals 1 over e times A0, where e, we remember, is natural number e, 2.78 something or other, right? So why is that useful, okay? Well, if I go back and do this same thing that I did here, right? If now I say the natural log of 1 over e of A0 divided by A0 equals negative kt, okay? Hopefully you can see what's going to happen here. This ends up becoming the natural log of e to the positive kt, all right? And the natural log of e is just 1. Oops, I did it again. So I'm going to say, instead of t, I'm going to write tau, because that's lifetime. That's the letter we use for lifetime, okay? And so now what we get here is tau, the lifetime, just equals 1 over k. So it's actually slightly easier to calculate, right? To calculate half-life, you go natural log of 2 divided by k. To calculate lifetime, it's just 1 over k. That's really easy, okay? And so what does all of that mean? Well, we recognize half-life is 50%, right? Well, as it turns out, 1 over e is roughly 37%. So 1 lifetime is 37% of A0, okay? Well, what happens when we have 2 lifetimes, okay? Well, as it turns out, 2 lifetimes, okay, so we'll say 2 times tau is 1 over e squared times E0. All right? And let's see. Oh, quick math. I used to be able to do that in my head. So 1 divided by E is 0.37. Okay, so 1 divided by E, let's see, squared gets us to now about 13% of the initial A concentration. All right. That says that's supposed to be a 2. It looks like a squiggly sign. So 2 lifetimes. All right. And so finally, 3 lifetimes, so 3 tau, is 1 over e cubed of A0. And that one, to my memory, is about 5%. So that's 1 divided by e cubed. Yeah, so now that's only 5% of A0 remaining. So why are these significant? Well, as it turns out, these scale the same way that standard deviations do. Okay, maybe you didn't know that, but one lifetime is actually equivalent to a standard deviation. 2 lifetimes is 2 sigma, 3 lifetimes is 3 sigma, which gets you that 95% of the reactant has decayed. Okay. So I think when it comes to first order reactions, lifetime is far more useful than half-life. Okay. Although the standard convention for especially nuclear decay is to use half-life, all right? That's just what happens. In atmospheric chemistry and environmental chemistry, lifetime is used a lot more than half-life. And again, it's just 1 over K, okay? So you should know that. Let's move on to second order. So I know I've been talking for about 25 minutes already. This is kind of a big lecture because we're going through these models and we're getting into the meat of this, okay? So now the first one that I'm going to go to here is talking about just the basics. So if we were to talk about a very simple second, actually not a simple one, for some reason I'm doing the more complicated one first. A plus B goes to C, okay? And if I were to write a rate law for this, some of those rate laws would look like the following. It would be dA by dt, and I'm going to put the negative sign in front of there, right, to get that stoichiometric coefficient correct. And I know that that's going to be the same as negative dB by dt, okay, which I also know is going to be the same thing as positive dC by dt, and all of that is going to equal K times A times B. First order in A, first order in B, second order overall. All right? And so I've got that set up here in the Mathematica model. And if we follow through that here real quick, check it out. Look, I've got A prime of t, so we know that's dA by dt, equals negative K times A times B. All right? So that's all good. So now we've got to write the rate for B. Okay? dB dt equals negative K times A times B. So it's the same thing. And then now finally, dC dt equals positive K times A times B, okay? And then for this model, so this is model 4, by the way. And you don't have to do a 4A and a 4B. So this is, again, my little extra to show you what's going on with second order reactions. So in here I set up A and B to be slightly different concentrations so that you could actually see them. If I were to put A and B as the same concentration, if they both started at 0.05, then it would just look like one curve on this graph, okay? And so now if you follow along here, look, we're solving our model for A, B, and C now, okay? And when I do this plot evaluate code, I have to evaluate it for A at time t, B at time t, C at time t, and then I replace it with this model for A, all right? So now this is a second order reaction, and if you've got a really good eye, you might pick up that these are exponential decays. And that is correct, okay? So in this second order reaction with A plus B, right, the profile of A, when I solve this differential, okay, will actually be A at time t equals A0 e to the negative kt. And this one, B, it is still first order just in B, okay? So it will also have that exponential decay. And C, of course, will be the positive of that, right? C will be it won't be to the negative kt. We'll work out what the product rate law turns out to be later. It turns out to be 1 minus e to the minus kt. Okay, but we'll work that out later on, because right now it's really just all about the reactants. And the Mathematica model is working out these for us. Okay, so there's exponential decays here. All right, and so what if now, instead of thinking it like this, because actually we can't even solve this by hand. If I were to now go through and try to solve this in the same way that I did up here, solving these differentials, right? this becomes exceedingly difficult. Atkins has the full solution of doing that, and you basically arrive that each individual reactant has a first order decay because they are first order in each reactant. So now what if we had a second order reaction that looked more like this? A plus A goes to B, okay? Or in other words, so I'm going to separate here. What if we had 2A goes to B with rate constant K? So first order in A, first order in A, so it's a second order reaction overall. And so now what that means is I can write negative dA by dt equals K times A squared. Okay? So now when I go to solve this thing, all right, so this one we can solve, no problem, okay? So when I go to solve it, it's going to be the integral, still same way we did it before, A0 and A at time t, and dA over A, all right? And let's see, I'm going to keep the negative sign here. You'll see why for it makes the solutions a little bit easier. Oops, that's, I wrote it completely crazy in my notes here. It's dA over A squared, and that's KT, okay? And so when I go to solve this thing, what I end up getting is the following. 1 over AT minus 1 over A0 equals, oh, that's K dt, right? Integrated from 0 to t. And so then now that all equals kt. And so rearranging now, if I plot 1 over at, so excuse me, that's 1 over at equals kt plus 1 over a0. And this is the linear form of the integrated rate law, where this is now y equals mx plus b. All right? And so what I should get out of a second order reaction with only one reactant, okay? When I plot now, let's see here. If I plot 1 over the concentration versus time, look, there's a positive number there. The intercept is 1 over A initial, okay? So it's not going to start at 0. It's going to start at some value, right? And it's actually going to go up, okay? And so my slope is still equal to K. And we should also, while we're here, let's actually work out the units of K just really quick, okay? So let's see here. I'm just going to give them to you instead of working this out, all right? So K for a second order reaction has to be liters over moles per second, or for our gas phase, cubic centimeter per molecule per second. So the units on first order versus second order reactions are different, and we have to pay attention to that. Okay, so here's what I got going on in my Mathematica model to really highlight these two differences. When you have a reaction that's so like, let me go back up here. Yes, first order in each reactant, A plus B, right? So I noted here, you get an exponential decay. But if you don't believe me, if you're looking at this and you're like, well, that could still be a 1 over concentration. It could. I don't have good enough eyes to tell that that's exponential. So what I did here is I created a manipulate model the same way I did above. And I'm manipulating the rate constant. And the reason why I'm manipulating the rate constant is because it really shows you the test, okay? And my test is, look, when I plot 1 over concentration, which I also adjusted in this model, and I did that by saying evaluate 1 over the concentration, okay? These should be a straight line with a positive slope. I see a positive slope, that's good. But look, as I manipulate this rate constant, that really shows you that this is not making a straight line. And so notice I'm plotting A and B here, and A and B are my reactants. I left off C on this manipulate model. But you can see here that this reaction, even though it's second order, it is not second order in A or B. It's first order in A or B. So technically, if I plotted the natural log of concentration versus time on this, now my A and B would have negative straight line slopes. Okay? And then to prove that to you, I made a new model, which again, you don't have to do. Model 4b, just second order in one reactant, right? A plus A, okay? So I just solved it for A and B, and when you look at this, you might think, well, that kind of looks like an exponential decay, and it does, right? My eyeballs aren't good enough to just look at that and know it's exponential. However, what I can do is test it, and I'm gonna test it by, once again, evaluating 1 over the concentration, because if I plot 1 over concentration versus time and I get that positive slope straight line, then it's definitely a second order reaction, and it's a second order reaction in one reactant. So here we go. So you can see already that's looking pretty good. And when I manipulate the K here to make it bigger, look at all of those values of K, it just remains to be a straight line. So it's definitely passing the test that this is a second order reaction. Okay? Second order in one reactant. With this A plus B situation, that can still most definitely be a second order reaction. However, it's first order in one reactant and first order in another reactant. Okay, I'm going to move on. So let's do time constants for second order reactions. And I'll just do this really quick because I want to end this video, okay? So now when I have A at time t equals 1/2 A0, that's going to give me my half-life, okay? And so I remember my rate law for, and this is just for a simple reactant, okay? I'm just showing you this for 2A goes to B. So we're just going to do the simple one, all right? Let's see. So yes, 1 over AT equals KT plus 1 over A0. So now when I substitute that in, right, I get 1 over 1/2 A0, and that equals K, T 1/2, because we're talking about the half-life, okay, plus 1 over A initial. And then rearranging and doing some algebra right here, I'm gonna skip through that. But what I end up getting, solve for T 1/2, T 1/2 equals 1 over K times the concentration of A. And this is how we also know how we can work out the units of K, okay, for the second order reaction. So for example, suppose I'm doing time in seconds, right? Well, I know my concentration is in mole per liter. So that's why this K has to be liters per moles per second, right? Because the liter and the liter cancels, and the mole cancels, and 1 over seconds equals a second, okay? So I think that's pretty good. I'm going to talk about pseudo first order reactions and their time constants, as well as, keep moving through the material in the next video. 40 minutes that I've been talking approximately, that's good enough. Okay, folks. Hasta luego.